Test, test. Can you hear me? Hello? Can you hear me? Yeah, okay. Great. So, good morning, ladies and gentlemen. Welcome to SIGCOMM and also welcome to workshop NetCompute. My name is Harry Liu. I'm actually not the chair of this workshop, but delegated by the chair of this workshop to host this workshop because the two of them have either a visa issue or some scheduling issue. So that I will start the workshop and by briefly introduce the programs and the keynote speaker. So as you can see, we have a keynote speech, and we have also 6 paper presentation, all about programmable switches, program hardware, and the whole workshop will be on the morning, and it is a joint workshop with the kernel bypassing networking in the afternoon. So because both of them are about the smart hardware, programmable hardware. So today we will start with the keynote speech. And let me introduce the keynote speaker, Professor Robert Soulé. Robert is an assistant professor at USI in Italy and a research scientist at Barefoot Networks. His research interests are in distributed systems, networking, and applied programming languages. And he was a postdoc at Cornell University and holds a PhD degree from NYU. And he was also a research co-op at IBM Research, Watson Research Center, and he's a winner of IBM Innovation Plateau Award, and a Google Faculty Research Award, and the Best Paper Award from ACM, DEBS, and Usenix and SDI. Welcome, Robert.
Hi, everyone. Thank you for the introduction, Harry. Great, so let's just jump on in. Conventional wisdom is that the networking is just plumbing. I mean, this is something we sort of is drilled into us, I think, since we're grad students. At least I make my grad students, I'll read the classic paper end-to-end principle. And, I'm paraphrasing it a little bit or simplifying the argument a little bit. But essentially what they say is, that the network provides transport and services should be at the ends. And people tend to believe programmable networks are either too expensive, too slow, or just consume too much power. Well, in recent years, this has changed. A new breed of programmable switches is now available. They're programmable. There's no power or and this is a barefoot switch, but there's many other devices on the market that offer similar sort of programmability and performance. So this raises an interesting question. If this trend continues, as has happened in other industries, we've seen again and again with GPUs, DSPs, TPUs, and ASICs, then programmable ASICs will soon replace fixed function chips and data centers over time. And if this happens, then what functionality belongs in the network? So it's easy to sort of look at conventional functionality, load balancing, firewalls, congestion control, and think, yeah, this makes sense, it belongs in the network. These are really functionality that's typically associated with networks. But the thesis of my talk is that we actually have a tremendous opportunity to put other services in the network. In particular, we can run important, widely used distributed services in the network. So to give some examples, we could have services for fault tolerance, key value stores, stream processing. So why would we want to do this? And the answer is fairly straightforward. If we put Paxos, consensus protocol, in the network, we get a 10,000x, that's 5 orders of magnitude improvement in throughput running this service in the network. If we put a key value in the store in the network, you can run a key value store that can process 2 billion queries per second with a 50% reduction in latency. And a prototype we did of a stream processing engine can process 4 billion events per second. So this all sounds great on paper, but there's a bunch of issues that need to be addressed. How do we actually program network devices? What are the limitations? What are the abstractions that we need? What parts of the applications could or should be in the network? What's the right architecture? And then finally, given that we're asking the network to do so much more work, how can we be sure that the services are implemented correctly? So these questions sort of span across multiple different areas. There's programmable network hardware, some ideas from distributed applications, and some ideas from logic and formal methods. So this talk is going to be at the intersection of all three of these areas, and it sort of outlines the broad outline of what I'm going to talk about. We're going to leverage emerging hardware to accelerate distributed services and prove that the implementations are correct. So the rest of the talk just follows this outline, so let's just jump right in. So first, to give some background, what is a programmable network? What do we mean by programmability? Well, typically, we know that the network is divided into two components we call the control plane and the data plane. The data plane is the part, the fast path that actually processes packets, and the control plane is the side that installs rules by which the data plane makes its decisions. So for example, if the IP destination address is 10.0.0.1, forward out port 1 is a control rule, and then the data plane is going to send packets out, send packets that match that IP address out port 1. So there's programmability at multiple layers. Here I highlighted some of my own work, but there's a lot of other work in this area. So at the control plane side, you typically have some sort of source language that then is compiled into a set of rules, like OpenFlow rules, and then you have some controller component that will install these rules onto the switch. So that's control plane programmability. Here we're more going to focus on data plane programmability. So with the data plane programmability, you have some source language. Here again, we'll mostly focus on P4. You have a compiler, and then the compiler will install these onto the device. Now, mostly I'll focus on ASIC devices here, but it could also be FPGAs, SmartNICs, NPUs, and other programmable devices. So the main abstraction for data plane programming is what everyone calls it the match action. Match action to actually fill in these tables with specific rules to follow. Now, the programming language abstraction of match action follows directly from the hardware. So in the hardware side, you have a match action unit. There's SRAM and TCAM for doing different types of matches, exact or ternary. You have different types of ALUs to do action. So you have stateless ALUs that have some limited instruction set, like arithmetic operations, bitwise operations, and you have stateful ALUs for counters and meters. And now these are all massively parallelized. So ideally, you could make all of your decisions just by hitting one match action unit, and you would data parallelize them to get the highest throughput. That's not always possible to make all the decisions, so you need some pipelining as well. And so what you end up is an architecture that looks roughly like this, where you have data parallelized match action units in a sequence of pipes. Now here I've only drawn two. In real life there's more than this. So this is what's called the PISA architecture, programmable ASIC architecture. What happens is packets arrive at on the parser side. They're parsed to extract the header. Then they're processed by the sequence of match action units. In the middle there's a crossbar. And then on the egress side there's also another sequence of match action units followed by the deparser, which is going to put the packets back on the wire. Now, the main language that's become dominant right now for programming these is P4 language, and the P4 language abstractions follow directly from this architecture. So in particular, you specify a header format, how to parse them. You define tables that match on header fields and perform actions, say like modify the packet or drop it. And you have some notion of composing these tables into a sequence. So this is really how you go about programming the data plane in P4. Now, there's also some constraints that are imposed by the target. So in particular, there's a fixed length pipeline. Like I said here, I illustrated two. In practice, there's more than that. There's a limited amount of memory available at each match action unit. And then you have dependencies on how you can access that memory. So just some quick observations about this architecture. So I described a specific piece of architecture here. The architecture is designed for speed and efficiency, but this performance doesn't come for free. There's a limited degree of programmability. The language is not Turing complete, and that's by design. Now, the other thing to notice is that we've seen multiple iterations of P4 language. There's been P4.14, there's been P4.16, there's going to be a P4 18, 21, and so on. The language may change, and the different hardware generations are going to change. You know, there may be longer pipelines, there may be more memory available, but fundamentally, this design is going to stay more or less the same. And that's just because of how it's designed for speed. You want to parallelize as much as possible the match action processing. Okay, so given that background, how can we think about using that type of hardware for co-designing networks and distributed systems? So the first question you might ask is, what sort of applications should we put in the network? I've been proven wrong about what things you might want to put in the network in the past, but in my work, I've focused really on what I consider the fundamental building blocks for building distributed systems. In particular, I've looked at a few different things. I looked at consensus, which is essential for building fault-tolerant and replicated systems. We looked at caching for maximizing utilization of available resources, data processing for doing some in-network computation analytics, and publish-subscribe, which provides semantically meaningful communication. Now, for this talk, I'm going to focus on the first one, mostly consensus. So, are you guys familiar with the consensus problem? Yeah. Consensus is the main problem is you want to get a group of replicas to agree on the next application state. It's a protocol for building, for supporting state machine replication, and they're the foundation for building fault-tolerant systems like OpenReplica, Ceph, Chubby, and many distributed systems problems, classic problems like atomic broadcast, atomic commit, can be reduced to consensus. Now, when we're thinking about how we can leverage the network to improve consensus protocols, there's really two different approaches we can take. One thing we could do is to start with the consensus protocol as is and try and push that logic into the network hardware. Now, then the other thing that we could do is that we can observe that consensus protocols often make assumptions about what the network provides for them. And if we could use the network to enforce a particular network behavior, then we might be able to redesign or simplify or optimize the consensus protocol in some way. And this is probably iterative. So another way of looking at this, I think, is to have these sort of two axes here. On the x-axis, this is a little hand-wavy, but what we did is programmability. So here, we maybe have weak programmability or no programmability all the way on the left, and maybe this is just forwarding packets and not doing anything else. And we can imagine that there's more and more sort of programmability available in the device. Maybe you can execute some operations, maybe you can have some state that you store, and so on. And then we can also, on the y-axis here, is sort of assumptions about what the network provides. So at the weakest level, it could sort of provide best effort delivery and nothing else. And at the strongest, we might imagine a network that has no message loss and FIFO delivery, right? So traditional Paxos, defined by Leslie Lamport, point-to-point delivery, and it doesn't have it doesn't make any assumptions about network programmability. Now, fast Paxos was an optimization that Lamport proposed, and it's based on the observation that under normal circumstances, packets arrived in order most of the time. He called this spontaneous message delivery. And when this happened, spontaneous message ordering, and when this happened, you could actually optimize away a step of Paxos and speed it up. And then if that ordering is violated, then you fall back to traditional Paxos. Now, you could sort of imagine a range of protocols that sort of explore the design space providing. And my first efforts in this area were in a protocol we called NetPaxos. So what NetPaxos, it's a little bit like fast Paxos to the extreme. We assumed that there would be no message loss and FIFO delivery. And if you make those assumptions, then you can have a very simple protocol that it greatly simplifies traditional Paxos. Now, the good thing is that 99.9% of the time the assumption's held, and if that happens, then you have a really fast consensus protocol. But really, 99.9% of the time is promising, but it really doesn't provide you consensus. 0.1% of the time incorrect is still a broken protocol. So really, this protocol that we published in SOSR, it's sort of not ideal. It's still broken. It's more of a nice academic exercise, but it wouldn't really work in practice. Now, I think there's been some great work out of the University of Washington where they sort of improved upon this original idea, where they said, you know what, we can use the network to try and increase the likelihood that we would have no message loss in FIFO delivery. And if that happens, then we can optimize Paxos. And there's a couple papers published on this idea, speculative Paxos and no Paxos, that really, they take the idea and make it more practical. And in particular, they find a way to resolve the case when the assumptions are violated. They fall back to traditional Paxos. Hard to pronounce that in a good way easily, but at least visually you can distinguish the talk. So here the idea is that we're going to make no assumptions about what the network's providing, but we're going to try and execute all of Paxos logic directly in switches. So why are we focusing on Paxos? Well, there's a variety of consensus protocols that have been proposed over the year, virtual synchrony and Raft or other ones, but Paxos is really considered the gold standard of consensus protocols. It's one of the most widely used, and it's been proven correct. I've heard this quote attributed to Butler Lampson. I haven't actually been able to find the exact reference, but he says there's two kinds of consensus protocols, those that are Paxos and those that are incorrect. So in our work, what we did is we moved Paxos into the network. This raises some questions. What parts of Paxos should be accelerated in the network? How to map the algorithm to stateful forwarding decision abstractions. In other words, can we reinterpret Paxos logic as a sequence of match action table lookups? How do we map the complex protocol to the low-level hardware abstractions? And what's the right interfaces? How do we deploy Paxos? And by interfaces here, I mean interface to the actual applications that are being replicated. So before going into more details, let me give quick overview of Paxos, one slide, Paxos in a nutshell. An execution of Paxos is called an instance. Each instance is associated with an ID that's called the instance number. The protocol has two phases. Each phase may contain multiple rounds, and there's a round number to identify the round that you're in. And kind of the high-level intuition is the phase one is all of the participants want to agree on what instance number are we talking about, and phase two is for that instance number, what value are we all going to agree on. And the observation here is that phase one does not depend on it sort of looks like this, is that, we run phase one in a batch and we declare a set of instance numbers we're going to use. Here I've illustrated them as n through m. And then we're going to have special Paxos packets that have a Paxos header that contains the union of all the Paxos messages. So it contains the type. This is identifying which message in which phase of the protocol we're sending, the instance, round number, vround, the voted round, and the value. So when the batch fills up, so packets arrive. When the batch fills up, we need to checkpoint, and then we re-agree on a new set of batches. So there's a trade-off here with performance and memory. So basically, the larger amount of memory that we use, then we can checkpoint less frequently, and we'll get a better throughput. This is one constraint that's often difficult to manage on a memory-limited device like the switch. Now, there's also some engineering difficulties here. You have to access dependencies, makes it a little bit tricky to implement a sort of ring buffer type structure in P4. So you need to sort of just use some sort of compiler hacks to trick the compiler into doing what you want. It's not really a real research contribution, but it's more just getting to know the details of working with the P4 compiler. Okay, coordinator sends broadcasts that value to all the acceptors that promise not to accept any more proposals for a given instance number. And then the learners get a quorum of messages from the acceptors, and then when they get that quorum, they deliver that value up to the application. So this is, from a high level, what's going on in phase two of Paxos. So what parts here should we accelerate? That's the question we looked at. And so what we did is we ran a little experiment to see what are the bottlenecks for Paxos performance. So here on the left-hand side, you see CPU utilization when we're trying to send at maximum throughput sending consensus messages, Paxos messages through. And what we saw is that the coordinator becomes the first bottleneck in the application. And the reason is it's because it's sort of the central point that's processing all messages. So all messages have to go through this. Then the other thing that we saw is that if we increased the degree of replication, the number of learners here, and granted we went a little bit out to the extreme, we went to 20 replicas, which in practice maybe you wouldn't have more than 3 or 5 replicas, but as we increased the degree of replication, then acceptors became increasingly a bottleneck as well. Their utilization increased. And again, it's because they're processing a large number of messages and multicasting them to all the learners. So our observation was that when you're going to accelerate Paxos by putting it in the network, what you should really focus on is the agreement part of Paxos protocol, which is the coordinator and acceptor roles here. Now, the next challenge we faced was how to map Paxos into the sequence of match action tables here. Now, so I don't want expect you guys to read this, but this is a snippet of Lamport's original description of Paxos. Now, Lamport's a great writer. He wrote very clearly, but it's not immediately clear how to map this algorithm onto match action units. So in our papers, we have pseudocode here for the algorithms that present the algorithm for the Paxos algorithm protocol in a slightly different way. And here it's more of an event condition action interpretation of the protocol. So when a packet comes in of a certain type, we match on it, we modify some header fields, and we forward it out. So again, you no need to focus on the details of the pseudocode here, but the paper our SIGCOMM CCR paper has all these algorithms for how the different roles map into this match action unit. So then the next challenge I mentioned for putting Paxos in the network was, what's the interface between the application and the accelerated parts of Paxos? And so, like I said, we're focusing on accelerating agreement. And so this draws a natural boundary between what the application does and the network side does. So the proposers are going to be on the application side. They encode a value in the special Paxos header. Then the coordinator and acceptors are running in the network. And they're, here, if they match, add a sequence number and forward, or the acceptors, if they match, compare the round number field in the header, update some state, and forward again. And then on the learner side is back to the application, where it's going to, when it decode the message, and it's going to return the value via callback up to the application when it receives a quorum. So the specific interface is just a C wrapper that provides the same interface of any other Paxos implementation. So with submit, deliver, and recover, to send a value, to deliver a value, or discover a prior value. And this is actually the same interface of popular libpaxos library, which is an open source implementation of Paxos that's widely used. And so you can have a drop-in replacement for if you want to use our network version of Paxos or P4 Exos versus a standard software C implementation. Now, how do we imagine it deployed? Well, we sort of imagine it deployed as sort of bump-in-the-wire processing. And so what a network version might look like is above here, where the proposer sends to a top of rack and an aggregate, and then eventually hits a spine that's acting as a coordinator. Another set of acceptors that are, aggregates are acting as acceptors, and finally to a TOR that sends it back up to the learner. And so we sort of see it's sort of one sending message all the way through the network versus typically where there's 3 round trips through the network from going to proposer to coordinator, back to acceptor, back to learner. So we can get an immediate just reduction in latency. Okay, so then do we benefit from this, right? What's the, do we get the performance that we'd expect? And we focused on 2 questions: what's the absolute performance and what's the end-to-end performance? So the end-to-end performance, well, the red here highlights what we saw. It's pretty nice. If you're just running on a Tofino chip and just measured in isolation, each of the Paxos roles, we're getting 2.5 billion consensus messages a second. That's a 5 order of magnitude improvement over a software implementation. And the data plane latency is less than 0.1 microseconds. And again, this is just measured inside the chip. It doesn't include the SerDes. It's just the data plane component. So this number sounds great. And then we actually tried to use it to speed up a real distributed application. So what we did is we took RocksDB key value store and we replicated it and kept it consistent using network accelerated Paxos. And when we do that here, this chart shows what happens compared to the software implementation libpaxos versus our network implementation. And we got a 4.3x throughput improvement over software and a 73% reduction. Now, 4.3x is nothing to be ashamed of, but it's not quite the 5 order of magnitude performance improvement that would seem to be possible by putting it in the network. And what happens is that the application itself becomes the bottleneck. So RocksDB couldn't process the number of consensus messages that we can send it. So it tops out about 250,000 messages a second. So as sort of a work in progress, what we're looking at is how can you restructure the application to take advantage of the accelerated throughput. And what we've thought to do right now is to partition the application state. This is still a bit of a work in progress, but you can partition the application state and you can run multiple Paxos instances in parallel in the network. And so here I hope I've illustrated this well. So we extend the protocol with a partition ID, and each of these are sort of each of the partitions ID are managed by a separate sort of instance of Paxos running on the switch, and then on the application side, each shard or partition state has a different agreement. And if there's no cross-partition requests, then you can sort of scale with the number of partitions and number of shards. And doing this, we can get here it's sort of frequency of checkpointing versus size of the charge, but we've been able to get up to 500,000 messages a second for a fully partitioned workload. Now, it does raise the question that, occasionally you might have requests that span, across these partitions, in which point you would need to add some barriers of synchronization. And like I said, this, that'll slow us down. But I think this approach is really promising. So I think there's an exciting opportunity here. If once we start accelerating services in the network, we can think about how we can redesign applications to take advantage of this, where previously it was the consensus itself was a bottleneck. Now the applications, we kind of threw the ball into their court, which is nice. Now, this maybe sounds kind of academic, I think, are people able to really use this? And in fact, actually, it has practical applications. So I'll just mention one. We started working with Western Digital, which is a storage company, that they've developed a new type of non-volatile memory. And this memory is called storage class memory, which has some really nice features. One is that it has a latency comparable to DRAM, so very low latency memory access. It's byte addressable, so instead of block addressable, so that's really nice. And it also is very inexpensive to manufacture, much, much cheaper than DRAM. So in theory, what you could have is instead of the traditional memory hierarchy of DRAM and SSD and then disk and tape and so on, you could replace that all with a really cheap, low latency, inexpensive memory that's very low latency. But there's a fly in the ointment that this type of memory wears out over time. So what we've been working with them is to actually build a sort of a main memory appliance where you have a bunch of these memory instances where you have replicas. We're going to treat the memory like a distributed system, and we run Paxos, or a variation of Paxos actually, in between these memory instances to keep them consistent. And when one fails, we still have the replicas to get the authoritative copy. Now, so this is a really nice way of providing, we can use really fast in-network consensus to provide sort of a memory, off-device memory appliance, and we're trying to aim to get a petabyte of main memory available using this. So I think it's really cool practical applications of this type of accelerated consensus. Okay, now to recap, I identified a whole bunch of different protocols here that sort of span the space of programmability and assumptions about network behavior. And for this talk, I really focused on one extreme, which is just to put the same Paxos protocol, Lamport's Paxos protocol, directly in programmable switches. So why I like this approach is because it's just Paxos. Now, consensus protocols are notoriously difficult to understand, notoriously difficult to get right. And by just focusing on Paxos, we know it's been proven correct. It's sort of the gold standard. We don't have to say, well, under these assumptions, it's slightly different. We can just rely on, we have some confidence in what it actually does. Now, but how can we be sure? I showed you we reinterpret the algorithm as this sort of event match actions abstraction. How can we be sure that it's implemented correctly? So now, proving the correctness, how do we know that we actually implemented this correct? So, this is probably an old story for anyone that's actually, ever touched the keyboard, is, we check the Paxos algorithm, our spin model checker, no problems. We wrote our Paxos code, we ran it in the network, and we weren't getting consensus. So there's a bug in our implementation. So the algorithm's right, we just implemented something wrong. Now, looking at this, verification of P4 programs is so tempting, like a hot donut available on the side of the road. Oh, I want to go grab it because P4 it's a limited non-Turing complete language, right? It's there's no loops, there's no pointers. The things that are typically associated with hard to verify aren't in the language. So to the extent that networks are verified today, the focus has really been on forwarding. But it would be really nice if, if we're going to ask the network to do so much more work, can we provide some method of verifying that what we're asking it to do is correct? So the problem with P4, though, is that, like I said before, we have this sort of data plane and control plane divide. And in the P4, we actually only have half the program. The control plane rules that are installed aren't there. We don't have that to analyze. And so really, we're trying to do program verification on half a program, and it's very difficult to do. So how do we approach this problem? Well, what we did is we have an approach based on Hoare logic. So if you're not familiar with Hoare logic, it's that you have axioms that capture relational properties of what is true before and after command execute. So if P holds and then we execute command C, then Q holds afterwards. So this is a standard approach to program verification. We can use an automated theorem prover to check that there's an initial state that leads to a violation, and then this will generate a counter example via a technique called weakest precondition. So how do we apply this technique to P4 where we're missing half of the program? Well, what we kind of want to do again, a hand-wavy sort of way is that what we want to do is take our P and then we want to augment it with some control plane assumptions and then say C and Q. So what we want to do is we allow programmers to express symbolic constraints on the control plane in terms of predicate on data plane state. And then combined, the control plane data plane behave as expected. So what are the challenges associated with this? Well, one is P4 does not have a formal semantics. So we actually had to define one, and we did that via translation here to logical formulas. Then what should our program annotations look like? Well, here, we're lucky that, I spent the last year and a half at Barefoot working with a team of networking programmers. And so here we just leveraged our domain-specific knowledge on defining what would be convenient annotation language. And then how do we make the solver scale? This is sort of the standard bane of program verification, is the state explosion. And here we leverage some standard techniques called passivization, which is like static single assignment, defined by Flanagan and Sachs from Popple, and we leverage those techniques to make our solver scale. So we have a tool here called P4V, and there's actually a talk later in the week by one of my co-authors that's going to go into more detail on this. I'll just give a little bit of the intuition here. So you start with a P4 program, you translate that P4 program into logical formulas, we define a program logic for P4, then you annotate it to check for certain properties. So one annotation might be something like, if the TCP destination port is 22, then drop the packet. And then we take the annotated properties along with our P4 program and we reduce it to an SMT problem. So for our Paxos example, what we might do is we add a desired property that says something like, if the round number of the arriving packet is greater than the stored round number, then drop the packet. Right? This is sort of the same technique applied to Paxos. And doing that, we actually found a bug in the pseudocode that we published in our CCR paper. So what happened is that here, what we said is assume that we have a valid Paxos header. And if you do, it implies that the stored round number is less than or equal to the round number that's arriving in the packet header. And then we apply the P4 table and we do some actions. And then afterwards, we want to, that we assume that if we still, we assert that if we still have a valid Paxos header, it's going to imply that we drop the packet. And this failed. And what happened is that we actually forgot to actually set the flag in one of our actions to drop the packet. Now, it's a simple, easy mistake to make, but we were able to debug it using this assert style debugging. So I think this was a nice application of verification in this case. So we ran our verifier on a diverse collection of 13 P4 programs. Some were conventional, for forwarding, router, NAT switch. We had source routing, top of rack, VPC, and then some in-network processing like Paxos and Linear Road, which is our stream processing application. And most finished in tens of milliseconds. Switch.p4, which as far as I know is the largest P4 program around, finished in 15 seconds. And I was very happy that I think we're the only system, that there's been a bunch of work on verifying the correctness of P4. I think we're the only system that's been able to verify the correctness of switch.p4, the program of that size. Okay, so what's the outlook? Well, to summarize, we have a system artifact that can achieve orders of magnitude performance improvements for consensus. We've identified techniques for programming within fundamental hardware constraints. We developed a novel reinterpretation of the Paxos algorithm as match action. And I think that, again, Paxos, there's been loads and loads of papers trying to re-explain the Paxos algorithm. Paxos made simple, Paxos made moderately complex, Paxos made practical, and so on and so on. I think in some ways, I'm hoping that our reinterpretation provides a different perspective and maybe adds some clarity even for distributed systems researchers. And then we have a mechanized proof of correctness of the implementation. Okay, so taking a step back, what are some lessons learned from all this? So what are some good candidate applications for network acceleration? I think here, and again, this is hard to exactly say, but I think if you squint a little bit, if it looks a little bit like routing, then I think it's a good candidate. In the Paxos case, you sort of squint a little bit and you say, okay, there's, you make some stateful decision and then you forward a packet to the next member of the protocol. It looks a little bit like routing. So I think that's a good candidate. There's other things like stream processing where you're doing filtering in the network. I think that's also a good candidate. It tends to be applications with transient state rather than persistent state, just due to the memory restrictions. Services that are I/O bound are good candidates. And then I think network acceleration helps with latency, but really applications with throughput are the big win. Now, okay, what's next? I think this is a very exciting time for networking and systems. Network programmability provides an amazing opportunity to revisit the entire stack of how we build distributed systems. You can redesign systems with an integrated approach, combining databases, networking, distributed systems, and programming languages. So I think there's a lot of greenfield area here to design, and I think part of this workshop is to hear more other ideas in the same area. So I'm really looking forward to today's talks. That's it. My website has pointers to papers from this work and these slides as well. So happy to take any questions.
Any questions?
Can you comment on the fullness of P4 as a language to deal with arbitrary applications or algorithms embedding the switches?
Sorry.
I mean, you work on P4. Somehow you were able to squeeze some portion of Paxos into P4 description. Can you comment on the fullness, on the expressiveness, on semantics of P4 as a general platform for writing these kind of algorithms?
Sure. So there's a few things that are just not possible to do right now in P4, like dealing with floating point numbers is quite difficult. There's no natural type for that. But I think from the networking community's perspective, I think the biggest thing that jumps out at people is it's a big taboo to have any recirculation. So you want to process packets and get them off the switch as fast as possible. Now, what I found is that in kind of trying to move some applications or protocols, algorithms to run on the switch, it's often necessary to do recirculation. And if you have recirculation, then it begins to look more like a complete language. You can sort of keep some state and recirculate it, and then you have much more expressive language. And so technically, it's possible to do these things. Now, I think now from the networking side, it's sort of a taboo. But if you put your distributed systems researcher hat on, say get half the throughput of 6.4 terabits, it's still 3.2 terabits a second is still really good and much faster than you get from a software implementation. So from wearing my distributed systems researcher hat on, I'm happy to give up the throughput for more expressiveness. So, but there's trade-offs like that you can make, and I think for moving applications, I think there's a great opportunity here. The other thing to deal with is how do we want to treat the sort of programmable ASICs? So one way to view them is to think of them as a network switch that does a little other work on the side. It's primarily network switch, but maybe it also caches some state for us that we can leverage. But another view to think you can take is to view this as sort of almost a sort of idiosyncratic server, a server that has some special properties. It's very good at I/O. It has a lot more SRAM than is typically available in a standard sort of off-the-shelf, data center server. Has a sort of particular programming interface. And if you think of it this way, and it's not necessarily dedicated for networking, but a specialized type of server that you can devote to particular application tasks, then I think it opens up the door to programming it for very particular applications, but at very high throughput. So I think that's how I'm increasingly looking at these devices. So I think that creates a lot more opportunities.
Hi, this is very exciting in general, and I'm interested in particularly in verification to verify the switch P4. Like, what kind of properties did you verify? Did you supply annotations, specify protocols?
Yeah, so there is some overhead, some burden on the developers that they have to annotate their code in an expected way. And this comes from, you have some domain knowledge about how you expect the application, how you expect the program to be used.
Right, but for, in particular for switch.p4, which is like the biggest P4 program, what kind of properties did you verify?
Here we verified some properties around MPLS labels, that they were processed correctly, or found some bugs where you would expect that sort of packets would be processed by a particular sequence of tables, and they weren't, depending on conditions, weren't always processed in the same order. But it wasn't sort of, I guess, here we sort of, I don't want to say that we knew what bugs to look for, but we knew the people that wrote switch.p4, and we sort of asked them to annotate particular behaviors that they expected from the control plane. So we sort of leveraged their expected domain knowledge on there.
Thank you.
Yeah.
Hi, Robert.
Hey.
Yeah, that was a great talk. So one of the questions that I had was, when I was working on some of the P4 programs, I don't know the current state of the art on this, but one of the advantages that is being touted for P4 is the ability, again, to compute within the network, and that could be stateful applications as well. Mm-hmm. Have you looked at how state is made consistent across the pipelines in the switch, and anything related to verifying the properties end-to-end on the state itself in the switch?
It's a good question. I haven't looked into that yet, but I think it's a nice open question.
Okay.
On a large network, we could have thousands of independent applications. How do you share the limited switch resources across them?
I'm sorry, I'm not sure if you're asking how to share the switch resources, limited switch resources against?
Across multiple applications.
It's a good question. It goes back a little bit how you sort of, one is I think you have to make some decisions about what sort of services you want to deploy and if they're widely used. So I think consensus is a good candidate because there's many applications that can take advantage of consensus. Other things might be sort of one-off for one particular application. Here, I don't know if there's a good rule of thumb, but you sort of just have to use your intuition. Is this going to be widely useful? Another thing is that, like I said, it's depending on how you want to use these devices. On the one hand, if they're mostly dedicated to switches and they have some, sort of value add on the side, like caching, then that's one thing. Or if you want to dedicate them to a particular task, that's another way that you could use them. So there's multiple ways you could imagine deploying them. And in the latter way, then it's sort of dedicated to a particular application. And in some ways, it can be much more cost efficient. So to give you an idea, we found out that my student implemented a publish-subscribe system in P4 that runs on a switch. And the publish-subscribe system, the throughput it offers, we did a benchmark against Kafka, Apache Kafka. Now, it doesn't provide, it's not apples-to-apples comparison because Kafka's providing some persistence and logging and other nice features. But in terms of throughput, it was about 2,000 Kafka servers versus one Tofino switch. And so, it's much less expensive, as long as you're willing to give up some of the other properties to deploy this. And so it makes sense to maybe deploy it as a dedicated box.
Okay, thanks to the speaker. So let's enter the paper presentation program. So the first talk will be presented by Sultana. Nick is a postdoc at University of Pennsylvania, where he works on programmable networking and DDoS mitigation. And he holds a PhD degree from University of Cambridge. And his talk is on in-network computing to rescue of faulty links.
Right, okay. Hi, good morning. I'm Nick, and I'm presenting on behalf of a sizable group of people at Penn and at Perspecta Labs. Let me just adjust this. There we go. Okay, so when two nodes on a network can communicate, that communication is predicated upon the existence of a viable path between them. But sometimes things don't always work out as we hope, and parts of the communication is lost. Packets are lost, and this leads to application malfunction. Now, there are various things that can lead to loss, and since failure is undesirable, it has been studied for a very long time, and one of the things that has been observed to lead to loss is network congestion. That is when you ask more than what the network can provide you with in terms of carrying capacity. And one of the features of congestion is that it is unstable. So if you back up from using the network for a bit, then things might clear out, and then you can continue using the network without experiencing congestion. And there have been various mitigations that have been developed for this problem. In this talk, however, I'll be talking about a different problem and addressing a different problem, which is corruption. Now, unlike congestion, corruption is not stable. Corruption means that packets in transit, because of some malfunction in a link or in an element, are being corrupted in a way that some upstream switch is going to drop them because they can't validate them. So this tends to be a stable problem, unlike congestion. So not using network for a while won't make the problem go away. And currently, the way of dealing with this problem consists of switching off malfunctioning elements and routing around them. So we find a link which is malfunctioning, which is dropping us some packets, and engineering the traffic in such a way that the faulty link is no longer used. And it is desirable to not use a faulty link rather than try to use it as much as you can, because this leads to more problems than one would like, especially with kind of higher layer performance. And this problem has been studied for a long time, and there's a lot of work that covers this. And we ran our own experiments to validate this for our own purposes as part of this work. And we were looking at the effect of loss on TCP throughput. And the main takeaway from this graph is that as loss increases, throughput drastically decreases. Right? So even with so if you have a little bit of loss, you're still going to observe a significant, appreciable drop. And the more loss you have, even if the loss is not 100%, you almost get 100% drop in throughput. So as I mentioned, the current solution to this is to disable links and move on. But this seems somewhat wasteful because these links aren't 100% corrupting. They aren't 100% useless. But we treat them as though they are, right? Better avoid using them than use them. So in this talk, we're going to try to make the best of what we have, to avoid disabling links if they are corrupting, but rather to use forward correction to make the most of what these links can provide us with in such a way that won't put off any higher layer behavior. And therefore, that would not cause applications to malfunction disproportionately. So in doing so, it's not that we're going to fix the problem. This is a mitigation, okay? This is a band-aid. The bit error rate is going to stay what it is for that channel. But by sending redundant information along, we are more likely to be able to recover some of the information that would have otherwise been lost had this mitigation not been in place. So what I'm going to talk about is a in-network solution which involves computing, hence the fit for this workshop. And it also builds on recent advances in programmable networks, right? So we need the network elements to be receptive to the sort of programming that would implement this mitigation. And the kind of networks that we have in mind are especially data center networks because of topology and throughput and equipment reasons, but there's nothing in this idea that necessarily restricts this to one type of network alone. Okay, so the design goals we have are to be transparent to the rest of the network. As Robert mentioned earlier on, one of the first things one encounters in networking is the end-to-end principle. And as much as possible, we don't want to disrupt what already works well, what already has been standardized and designed and tested. Naturally, given that the application, the network has finite resources, we don't want to use more than we should to provide this additional protection. So we want to be low overhead beyond the FEC's own overhead. So I'll be talking a bit more about that in the coming slides. We also want low complexity activation, right? We don't want some kind of complex coordinating logic between various parts of the network to realize that we have lossy links and to counteract that. So we'd like to go to as simple as possible kind of logic. And also for the sake of being pragmatic and realistic, we want to support different traffic classes because we might want to prioritize certain traffic over others in terms of the redundancy we might want to offer them and the latency that the FEC, the effect of FEC on latency this would have. Okay, so where are we going to put our intelligence? And the current state of the art places the intelligence to decide whether there's a problem and what to do about the problem in a central location. So it kind of gathers information from the network and then decides, okay, based on the information I have, this is where the problem is, and I will effect changes in this network to counter that. So we want to go to the other direction, to distribute this, to make network elements autonomous, to decide for themselves if there is a problem and what they should do to settle this problem. And as a side effect, the advantage that this has is that you get faster reaction time. So this can happen much quicker than polling the whole network and then deciding on what to do, and then, reconfiguring the switches to disable links. Another important question that comes up is, what do you do about lossy links? And I've mentioned that we're going to use for their correction, so we're going to put redundant information on the link in such a way that for a block of packets, we can reconstruct missing packets. But an alternative would have been to repeat, right? And I'm putting this slide up in the context of what I described about TCP earlier, because higher layer protocols that want to provide reliability already have mechanisms for providing that reliability, right? And in the case of TCP, it's an ARQ based on repetition. And we don't want to replicate that behavior at another layer. Another question that comes up, given, okay, we're going to go with FEC, we're going to have certain redundancy in traffic. At what layer do we implement it? And the choice comes up. So we discounted implementing FEC at the physical layer because, well, for one thing, FEC already exists at the physical layer. So recent standardizations of Ethernet do have FEC at the physical layer, but it isn't engineered in such a way to mitigate the sort of loss that we have in mind in this project. So it is engineered to meet different ends, right? As performance increases, even small physical problems can lead to loss, and that is the envelope within which it works. We are working within a scenario involving much higher loss. We could have FEC working at the network layer, so end-to-end. And intuitively, this would lead to loss because the ends can be far apart, and even if you have one lossy link along the way, you would be paying the price of that lossy link across the whole path. So that was our intuition. We carried out experiments on an S3 to validate this intuition, and we got what one expects, that the overhead can be quite punishing for end-to-end FEC. So we went with link layer, and this localizes the band-aid rather nicely, that if you have a faulty link, then that is where the error correction should be applied to by the adjacent switches. And this is a sort of deployment we have in mind. So it would be a kind of a switch to switch. And these switches need not be kind of linear, as shown here, right? So you can have a hierarchical fat tree arrangement. So the design we have in mind is for switch to switch links, but there's nothing that restricts it to that sort of design. If you have at greater expense, if you have smart NICs that can be programmable in this way, then the protection can also be extended all the way to the hosts. So let me talk a bit about the scheme, about the protection that it provides. So I'll introduce some keywords here, but the description will be fairly intuitive. So we have data that's crossing a link, and some of that data might be lost. So in order to mitigate for that, what we do is we add some redundant information. This redundant information are parity frames that are computed from the data that has already crossed the links. And this redundant information, in addition to the data that has successfully crossed the links, can be used to compute the data that was missing. Okay? So we have a threshold-like scheme that up to a certain number of loss, we can recompute the information that has been lost. We can do that exactly. So the parameters to the scheme are, there's a certain number of data packets, K, and a certain number of PERT packets, H, and together these form a block. So you might remember I mentioned latency earlier, so we do have to, we do tune these sizes according to the block size, according to the latency that we wish to keep up, because the bigger the block size, then the longer we have to wait until either we decide that the packets are not coming, or until we receive the parity packets. And this also motivates the need for different traffic classes. Okay, so do keep in mind, so we have some number of packets, some number of parity packets, and together they form a block. And let me just jog you through the intuition of how it would work. We have packets arriving, crossing a switch, and happy ending to the story. But if the link happens to be faulty, packet arrives, tries to cross, it's been corrupted, so the checksum can no longer validate, and the upstream switch drops the packet. What happens is that this leaves a mark. So these switches have counters and have monitors locally that can be polled to find out whether anything is anomalous. And this is what the current state of the art uses. So switches are polled for this information to find out if anything is not quite right? And our scheme does not change this. We rely on the same sources of information to detect anomaly, to detect failure. So what our scheme changes is that instead of detecting and reacting to this remotely, we do it on the switches themselves. So what happens in our scheme is we tag traffic before it's going to cross the faulty link. This also communicates to the downstream link that it's receiving, that the link is suspect. And data that manages to cross it is untagged and sent on the way. For data that does not cross the link successively, well, there's nothing we can do about it then, but eventually remember that we're going to be sending, after the K data frames, we're going to send H parity frames. So the program on the switch emits this parity frame, and we'll send it over, and based on the data that has already arrived, the missing information can be computed and sent along. Okay, so let me expand a bit more about what's in the tags. So we have a traffic class. So this traffic class is configured by the operator. I'll say a bit more about that in a second. Let's see. N is an index within a block, and we also have a block index to protect against bursty losses. In this example, you can see the middle 4 packets have been lost, and without the block index, we would not have realized that we lost those contiguous packets. Without the block index, it would have seemed like, yep, from n equals 0, we've gone straight to n equals 1. So as I mentioned earlier, the block here consists of K data frames and H parity frames, and the traffic is demultiplexed into different traffic classes, which can have different block sizes to them. And this traffic classification is based on the protocol imports, and it happens within the confines of even a programmable switch of the kind that Robert described earlier, because there's nothing extensive in this sort of computation that's needed. The extensive computation is needed in the FEC part. So picking up a bit on a point that Robert made earlier, so one has to make do with what one has in programmable networking, and for best performance, one has to be very frugal in the sort of computation that one can implement, and also kind of shoehorn that computation within the means that are available. Now, for this sort of traffic classification and kind of high-level logistics, P4 style programming is sufficient. But for the deeper part, for the forwarder correction, where you need to go into the payload and compute across packets, that requires retention of state that exceeds what P4 currently provides, and indeed that exceeds what the ASICs currently provides. So our implementation tries to make the most of what we have. So we rely on P4 for the bits that can be done in P4. For other bits, we write in a general purpose language in such a way that can target two programmable targets, one of which is CPU, which is uncontroversially programmable, and the other of which is FPGAs. So by targeting FPGAs, we are relying on a model where we'd have a more programmable fabric in the network that, however, unlike CPUs, would not require us to give up throughput because of the overhead that they incur. Okay, so we have kind of a two-part implementation. The P4 part, which involves the high-level logic and kind of limited state management and configuration, and the external logic written in C, targeted for the different chips. And this is work in progress work, so we have the encoder working and tested. I'll talk about that in a bit. And we also have we have the system working on CPUs, and the work in progress part are the state gathering from the Mac and the hardware decoding. So one of the most kind of tricky but also exciting parts of this work has been integrating the different layers together. So in the hardware implementation, what we have is a pipeline that goes from the Mac back to the Mac via the P4 logic and going to the external function, which is the FEC encoder. And one has to work with fairly developed tools in the space. So we worked on, we're using Xilinx's toolchain for this. So we use this DNet. It takes us from P4 to RTL, and this interconnects with the RTL generated from the FEC's implementation from C via HLS. And this is part of our ongoing work, is to kind of improve this facility to make it easier to to integrate more externs in an easier way, and not only in one target endpoint, but also in several across the network. So I'll talk a bit about the evaluation that we've done. So this involves unmodified host stacks and implementations, right, and applications, right? Trying to interfere with as little as possible with the end-to-end principle. So in terms of row throughput, we evaluated that on both targets, so both on the CPU and on the FPGA. We used the PDK to generate traffic. And we used the same implementation of the encoder in both the CPU and also in the FPGA. The intuition that we'd get better throughput using the FPGA was upheld. So we're using 10 gigabit links here, and so we saturated or close to saturated the 10G link for the FPGA. The CPU struggled, but we in our design we see the CPU as a fallback. That's if you have lots and you want to use the FPGAs for some more high priority work, then you can always degrade and drop things over to the CPU for processing. At a cost, but also at a benefit. You get to choose how to prioritize your work. So we also implemented the model using the wedge switch, implementing the Barefoot hardware, where we modeled what things would look like when both the encoder, which I described earlier, and also its matching decoder are in place. So what should we expect to see, given some varying amount of loss? So this model was implemented in P4, and we used iPerf to generate traffic for it. So this is a bit of an eyeful, but I want to draw your attention to the blue line with circular vertices at the very top. So that is the situation where there is no FEC. And on the x-axis we have loss. Loss is increasing as you extend towards your right. And on the y-axis you have throughput. The higher, the better. And as you will notice, with no FEC, throughput drops pretty quickly when you have But in comparison, so throughput grows, it drops pretty quickly when you extend loss. And in comparison, this drop is held back when you have FEC. So these pairs of numbers here are the K and the H parameters that you will remember from before. So what 25.1 means is that for every 25 data frames, we are sending one parity frame. This means that we can mitigate a loss of up to 1 frame per block of 25 frames. So even with a little bit of mitigation, you can already see a marked effect in the kind of performance you can otherwise not get. This is for iPerf, so this involves TCP. And the more you pay, the more you get, right? So looking at the brown dotted line in the middle there, that's for 100% redundancy. So for every 5 data frames we send out, also send out 5 parity frames. So you give up a lot of throughput because the FEC incurs a lot of overhead. But you also, if the link happens to be very lossy, you also gain significantly. And this is also matched up when we look at the congestion window size. So you see the congestion window size collapse in the blue line with the circular vertices, whereas it holds up for longer with the when FEC is being used. Okay, so let me wrap up. So in the talk, I talked about an in-network computing solution for mitigating lossy links, and this involves 2 bits. One bit is the logistical part, which P4 seems to be, and the P4 ASIC seems to be a good match for. The other bit is the kind of more stateful, kind of heavier computing part, for which we break out to external devices. The design goals were to be as intrusive, to be as unintrusive as possible in the current network, and offer distributed implementation for quick correction times. Now, this is not incompatible with existing solutions. Indeed, it is complementary to that, because, as I mentioned, you can't fix physical problems. Ultimately, you need to replace the equipment, right? That's dodgy or adjust it. So the existing centralized approaches work very well at a different time scale to alert an SRE or some engineer to go and look into the problem. But this buys you more time to better use the faulty channels until that happens. And as I mentioned, in ongoing work, we are completing this implementation and integrating new externs and having a facility to use these externs in a heterogeneous network. So with that, I'll stop, and I'll be happy to answer any questions.
Hi, Nick. Thanks. I really enjoyed your talk. I was wondering if you'd given any thought on how to extend the design for multicast traffic.
Right. Yeah. So one of the, as also you mentioned, I think in reaction to the first question you had. So our thinking has kind of bounced between what can be done in P4 and what we'd have to give up. So I think we haven't thought about multicast traffic. But if we were to, I think we'd first try to see to what extent that state of the multicast group could be kept in the switch to avoid having to pay the price of delegating information which would not necessarily need to be moved to a lower performance device to be moved there. So no, I don't immediately see the motivation for that, given that this is implemented in such a way that would be oblivious to multicast if it's happening at layer 3. So this would carry that regardless, because it's oblivious to whatever is at the higher layers, right? But if it's at a layer 2 layer, then yeah, that might require some more engineering, perhaps.
I have a question. I know that you used Reed-Solomon as your code. Didn't you think of using something better?
Right. So that's right. We use Reed-Solomon, and I'm not sure what you mean by better, since it's...
Well, Reed-Solomon is also okay. I will get into a tutorial on codes, but it is a block code, and so you have to wait for all of the block to happen before you can start decoding. Yeah. So there are things that actually you can do this better. Like actually you can decode as packets arrive or as frames arrive, and it's also it's a standard, the Reed-Solomon. It's a maximum distance. It's really great, but there's so many other codes now that are available that are more linear and would probably give you as good a performance with much less complexity. Right.
So I think this was a constraint in our design, which we worked with industrial partners. So we don't have. So I think it's quite possible that the computing part can be replaced with a scheme that is more amenable to specific requirements.
Yeah, because I would recommend it, because I think your results would probably look better.
So in terms of throughput, because you don't have to rely on blocks. In terms of throughput,
yeah, and in terms of complexity, you're doing this in P4. So having things really more linear, could probably go better.
So, see, I'm not sure you can do this in P4, because you'd have to do the computing on the entire payload.
Okay, so I read the paper, so maybe I misinterpreted it. But anyway, so I think if you do this, there's better implementations.
Sorry, anyone who has questions, you can talk to offline, because we're running over time. We have to move on. So let's thanks the speaker. Okay. So the next talk. Okay. The next talk will be given by Cristian Bennett. Cristian is a PhD candidate in computer science at Karlstad University, Sweden, and his research is focused on SDN, data plane programmability, and traffic engineering. And the title of his talk is Multipath Congestion Aware Load Balancing using Programmable Data Planes.
Okay, good morning, everyone. My name is Cristian. I'm coming from Karlstad University, and I'm going to present our work, Multipath Transport Layer Aware Load Balancing for data centers using programmable data planes. This work has been done in collaboration with Brown University and Ericsson Research Group. Which is our motivation? Nowadays exist many paths from source to destination in data centers with the aim to provide more bandwidth. However, just 25% of the core links are highly utilized, and this is because the traffic at the end is volatile and unpredictable. So some applications such as Siri try to highlight or try to use multipath transfer protocols to increase their performance by aggregating the bandwidth and provide more reliable connection. If we put on top of that some topologies might be asymmetric or might be symmetric but might have link failures and became asymmetric, so at the end we have a complex decision to make a good load balancer. In the history, we have seen several proposals as a load balancer, starting by ECMP, Let's, Conga, Hula, Drill, Clove, and many others. At the end, each of them works in different granularity, from flow-based to flowlet-based, packet-based, congestion-aware or not, maybe designed in a specific hardware or silicon chips, maybe programmable in P4 as Hula, more or less scalable, but at the end, they don't provide a multipath transfer protocol. So at the end, this is what the customer wants. The customer wants to aggregate the bandwidth and wants to have a reliable connection. So this is the aim of our work, try to help the customer to have what they want. Which are the main challenges of the load balancer. The first thing you need to have is accurately and faster detect congestion on the links. The second thing, have a robust against reordering. We don't want to mess up the connection of our clients. The third thing, we want to deal with asymmetries or link failures. And the fourth, it needs to be scalable. I want to give a brief summary of HULA because this is the base of our work. HULA is a load balancer that works in the flowlet based, and flowlet means that we have a burst of packets separated by the constant of time, and at the end, if this constant of time is high enough, we will not have reordering, and this is what we want, to don't have reordering packets. At the end, it's a solution that is done in programmable data planes, so it's a flexible solution, not done or designed in a specific silicon chips. And to deal with the large forwarding entries, it just monitors which is the best next hop. And how it does that? It sends probes packet from the top of rack to the other top of rack, and in those probes, it carries information about the utilization. So at the end, we have two things with these probes. We know which are our next hops, and we know which is our best next hop because we have information about the utility or the congestion. So at the end, how we face these challenges with HULA, and that's why we pick as our base work. The first thing we said, we need to fast and accurately detect the congestion, and this is done through the proving packets. We want robust against reordering, and this is done through the flowlet switching. We want to be efficient in asymmetries and link failures, and this we achieve with the proving packets again, since we have a keep alive. And the last, we want to be scalable, and this is possible because instead of tracking all the possible paths from source to destination, we just keep track of which is our best next hop. But at the end, we still have the same problem as we mentioned before. We don't have information about our multipath transfer protocol. And why? Because when the TCP's connections reaches the switch, at the end, the switch just sees two independent TCP connections with different IP sources and IP destinations. But at the end, these two independent TCP connections are subflows that belong to an MPTCP connection. So the problem basically is that the switch doesn't have contextual information about the MPTCP connection. So let's put an example of why this is a problem. Imagine two subflows coming from an MPTCP connection, reaches the switch. As we said, we have a table that says which is our best next hop according to the congestion that we have in the network. And it says that the best next hop in this time is port 0. So both subflows are sent over port 0. At the time these flows are running, of course, we update this best next hop, and now the best next hop is 1, but still, of course, we are sending over port 0 because the flowlet didn't expire. What happens if one of them expires? We rewrote it over port 1. Here we're happy, but what happens if the next flowlet expires of subflow 1? That again, we send it over port 1. So at the end, we have that some of the times, both subflows are run over the same path. And this is not what we want. As we said, we want to aggregate the bandwidth and provide redundancy and persistence because this is what the client wants. So what we need to do instead? So to do that, as you might imagine, instead of tracking just the best next hop, we need to track multiple best next hop to reroute the subflows over different paths. So for this, we extended the base of HULA for not just tracking the best next hop, but just tracking the k best next hops. The second thing we need to do to reroute the subflows over different paths is, of course, to identify that these subflows at the end, they are not independent TCP connections, but depend on an MPTCP connection. And this is possible to do that on top of racks or hypervisors, and later on we will explain why. So at the end, we need also to mark the traffic to help other switches to identify that this traffic belongs to an MPTCP connection and to which subflow it belongs to. To understand the main problem, I will just give a brief summary of how MPTCP works. Imagine we have an MPTCP connection, one subflow, we have the 3 handshake messages. The first thing we do is send from the sender the key of the sender. The receiver sends its key as well. So we have now the key of the sender and the key of the receiver. So when we start a new subflow of this MPTCP connection, to authenticate that this subflow at the end belongs to this MPTCP connection, we generate a token from this key, and then we can authenticate that this subflow at the end belongs to this MPTCP connection. But what happened? That these 3 handshake messages at the end can travel through different switches. So not all the switches might be aware about these 3 handshake messages. So that's why we selected the top of rack or hypervisor, since all the messages will travel across this switch. And to do that, to identify and to have this contextual information about MPTCP, what we need to do? We need to do 4 steps. The first thing is to parse all these 3 handshake messages, so we get all these keys. The second thing, we need to identify which MPTCP connection it is, and to do that, when we open a next subflow, we can know it generating the token that MPTCP is generating. And the third thing is to correlate how many subflows this MPTCP connection has. This is possible using P4, since, for instance, to generate the token, we can do that using external functions. We can parse any kind of header, so it's possible to do that, and we can write a stateful memory, all the information we need to do that. And the fourth step, as I mentioned, not all the messages, all these 3 handshake messages must travel through all the switches. So at the end, to help other switches that might be in other layers, we mark the traffic with information regarding the MPTCP connection ID and the subflow ID to help other switches to get the best decision. And to do that, we add an extra header that is, and we took this decision because it's really easy in P4 to add extra headers to add, remove, or modify these headers. So at the end, the client is transparent and doesn't know that what we are doing with the packet. Now I'm going to explain a little bit how we find out which are our best next hops, and this is an extension of the HULA paper. I will give an example. It's much easier to see. Imagine a top of rack that is sending probes messages, as we said, to detect which are the next hops and which are the congestion on those links. So top of rack 10 is sending 3 probes messages through all the 3 interfaces that it has. So it travels through S2, S3, and S4. So at the end, when top of rack 1 receives all these probes messages, it sees that the probe coming from S4, it has a max utilization of 50%. When it comes from S3, it has utilization of 60%, and when it comes from S2, it has utilization of 80%. So now, top of rack 1 can pick which is the best next hop to top of rack 10. And in this case, you will pick the lowest one. So you will pick S4. So you will pick S4 and you will store it in our best next hop table. The second best is S3. So you will store it in the second best next hop table, and so on and so forth. So when it comes to the packet, the flowlet, you do a hash. And based on these best next hop tables, you will reroute the packet according to this decision. And I will show an example to see more clear how does it work. As we said, imagine that we have a top of rack. It has an MPTCP connection running on. We said we will tag this subflow with information about the MPTCP ID and the subflow ID. So we will send it over S4, since this is the best next hop table that we have. What happens if we have another subflow? If we have another subflow, we will tag again, as we said, with MPTCP ID and with the subflow ID. And since the best next hop table that was S4 is already taken, we will go to the second best next hop table, and we will send it over S3 because this is the second best next hop table. If it comes a third one, we will send over S2 because the first business hop and the second business hop are taken, so we will go to the third table. So we will send it over S2. In case we have a fourth one, what we will do is using a scheduler like round robin and go again to the best next hop table, S4, and so on and so forth. In our evaluation, we propose a fat tree topology using 40 gig links and 10 gig links from the top of rack to the host, two kind of traffic, data mining traffic and web search traffic, and we use NS2 as the main simulator. We use MPTCP coupled congestion control and MPTCP uncoupled congestion control. And what we do is basically try to increase the load in the data center and see how it behaves, the traffic, measuring the flow competition time. So as we can see here, when we have 50% of load, and we take the graph with, we have all the flows, mice flows and elephant flows, we can see that we have a reduction of 21% if we use MP-HULA compared to the normal HULA solution. If we take into account just small flows, we can see that for the same amount of load, we have a reduction of 24%. At the end, if we look, for instance, at 90% load, when we look into the average of all the flows, we have a reduction of 34%. And when we look into the small flows, the mice flows, we have a 45% reduction. If we look into the uncoupled congestion control, and we look again on the 50% load, we will see now we have a higher increase because now at the end, each subflow is independent one from each other, so they don't try to get a fairness. So here we have a reduction of 54% compared to the normal HULA. And if we look into the asymmetric topology, and for asymmetric means the same fat tree topology, but just turning off one of the links from the core to the aggregation link, we will see that we have only 13% of reduction, and this is because, of course, we have one link less. If we look into the 90% load, for all the flows using uncoupled, we have still a 15% reduction, and looking into the symmetric, we will have a 32% reduction. So at the end, we can see that it might benefit to take into account which is the multipath transfer protocol that the client is using. To finalize, as a conclusion, we can say that we use programmable data planes to highlight the multipath transfer protocols of our clients. We use probes to detect which are our k-best next hops and to detect the congestion of the links. We can say that we use programmable data planes because it's more flexible. At the end, it's much easier to modify or to extend any other solution. And as a summary, we can say that we perform much better if we look into the flow competition time compared to HULA. So we beat in 1.27% or times at 50% load and 1.5 times at 90% load. As a future work, we would like to implement this MP-HULA and test it on P4 switches with Metronome or NetFPGA cards, and maybe test it over another multipath transport protocol such as MP-Quick, and at the end also maybe have a better load balancing logic, so instead of sending each subflow over first, second, and third, take into account other metrics such as the latency or congestion. And that's it, thank you.
question.
Hi, thank you. Very interesting. So how much of your performance improvement that you see on the tail latencies is due to actually tracking k best paths instead of just one path?
So you want to know what is the improvement if you increase the number of Ks?
There are two metrics here that are contributing to your performance improvement. One is that you are tracking k unique paths instead of one path. And the second is that you are distributing on a subflow basis instead of on a flow basis, right? So I'm asking about the first one. Because if you have k unique paths and you don't classify as subflows, what is the level of performance increase that you would see? Is that something that you looked at?
Okay, if you increase the number of subflows and you keep the k in the same value, you are meaning, isn't it?
Sorry, I'm comparing the previous paper on HULA, which is, there you kept, the paper keeps track of the best path. And now you're keeping track of the k best paths, right? So you have more information about the network, you have better visibility into the network. And so the question is, in the performance analysis, how much of the performance improvement is because you are tracking multiple paths or congestion state of multiple paths?
Okay. So you can see here in any of the graphs, we use two subflows and k equal 2 because at the end we have just two disjoint paths in this k equal to k2 topologies that we use. So if we go here to this topology, you can see that at the end we have just two disjoint paths. So we pick k equal 2, and at the end we use just two subflows. And you can see the difference between using just two subflows running over HULA approach and using MP-HULA that uses the same two subflows but rotate over two disjoint paths. So at the end you can see that in general it's much better because at the end you can aggregate the bandwidth over the topology.
The last question.
I quickly wanted to say that I think in this case, I don't think it makes sense to compare in that manner because even if you have k best paths and if you're using original HULA, you won't use anything other than the best path because it's just one flow. So Cristian, hi, it's nice to meet you. I'm the author of HULA, so it's kind of interesting to see how you extended it for MP-TCP. One question that I had was that if you look at the Conga, HULA, cloud papers, MP-TCP does pretty well compared to, in comparison to all these schemes, as in nearly on par. And I'm not surprised that if you extend that to include congestion being, the subflows being congestion aware, it does slightly better. But one of the concerns that was raised in all these papers is incast, right? The notion that when you have multiple subflows and they keep ramping up at the same time, and then if you look at typical incast data center workloads, it just goes haywire, right? So what did you notice for such that kind of behavior in your experiments? Or if you haven't done it, I would highly recommend doing that.
In fact, we then tested with like 1,000 nodes to check the impact on the incast problem. So I don't know what it will be the problem, but at the end, if you start several TCP connections, it will be as the same as using MP-TCP with two subflows, right? If you start two TCP connections.
Let's take it offline. I think the ramping up issue will still be there, is my worry.
Okay, let's thanks to the speaker. And also conclude this session, and the next session will be start at 11 o'clock.